Hello and welcome to the Cambridge Wireless Heritage SIG talk on the history of time and timing in telecommunications. My name is Andy Sutton. I'm a network architect within BT. I'm also a Heritage SIG champion within Cambridge Wireless. So today's talk will introduce the need for timing in modern cellular networks from the context of initial requirements for GSM. Being a Heritage SIG, we'll look at how that was implemented on an early base station. In this particular case, it will be the Nokia DF12, which was GSM 1800, second generation GSM BTS. We'll talk a little about base station oscillator modules and how they evolved over time. And then we'll introduce the concept of taking time from the transmission network. So in particular, the concepts of pulse code modulation and the 2 megabit per second E1 frame. We'll then cover GSM terrestrial interfaces and see how that E1 frame was used to build the GSM network before introducing the synchronization supply unit and its use within the mobile network. Carrying on further, we'll introduce the concepts of 3G and see how synchronization changed with 3G, and in particular the introduction of ATM as a transport network layer. We'll then talk about converged network sync for 2G and 3G before we introduce 4G and the requirements of LTE, LTE Advanced and LTE Advanced Pro, and then look at what's happening with synchronization as we evolve 4G networks and we move beyond 4G to 5G. And we'll then summarize the presentation. So the GSM radio interface is TDMA based, time division multiple access, and the photograph here is a traditional GSM 1800 base station from the kind of early to mid 1990s, and this is based upon space diversity reception on the receive path. So one of these antennas will both transmit and receive, the other will receive only to enhance the uplink. We have a microwave radio link here for backhaul, and this microwave radio would have carried typically a 1E1 circuit, so 2 megabit per second circuit, of which n times 64 kilobits per second would actually be utilised for the Abis interface, so the transmission from the BTS to the BSC itself. And again, we'll explore that Abis interface and how it used the 2 megabit frame and how that links in with the story of synchronization as we go through today's presentation. Key thing to pull out from the slide here is the gross data rate on the GSM radio interface of 270.833 kilobits per second. And we'll see reference to that kind of data rate in the frequency context very shortly, and then we'll start to understand why we use the particular frequency of oscillator that we do within GSM. But effectively that means that there's lots of overheads, as you would expect on the radio interface, above and beyond what, for example, would be utilised to support a full rate speech time slot of 13.6K. So looking at that DF12 base station, this is an example from Nokia. You could pick out similar examples from other major suppliers, the likes of Ericsson, Alcatel, Nortel, etc., who all provided base station infrastructure in the day. I'll just talk through the base station itself. We've got the kind of station unit at the top. So the three cards here make up the BIE, the base station interface equipment, and they terminate the 2 megabit incoming circuit and split out the various time slots and sub-time slots for transmission of the Abis interface. We've then got an operations and maintenance unit. Now for those who look closely, you'll see that I've blanked out a card here. You can just see the top of it. That's simply a card that was slotted in an incorrect position in this particular case because this was in a lab environment. So just ignore that position there. That wouldn't actually be occupied in a normal configuration that Orange deployed in the UK when this particular base station was being installed. The actual card I've highlighted here, this is the clock card itself. Now this is an MCLP, so this is taking a reference from the incoming line. We're actually going to talk about an earlier version of this card first, and then we'll come back to look at this line-fed card. We've then got some RF test equipment and two frequency hopping units here. One frequency hopping unit for the primary receiver, one frequency hopping unit for the diversity receiver as well. And then a couple of external alarm and control boards. Moving down to the lower shelf, we've got the power supply here, which is for the station unit. And that station unit could support multiple GSM transceivers. In this configuration we're showing a single GSM transceiver, so this would be an omni configuration, where we've actually then got the power supply for the transceiver itself. We've got 2 digital signal processing cards, each of which handles 4 of the 8 GSM TDMA time slots on the radio interface. We've then got a frame unit control board that actually connects back up then into the base station interface equipment. We've got the transmitter itself and the primary and diversity receivers. Now you'll notice a few red lights on here. As I mentioned earlier, this is a piece of test kit effectively within a switch site. So at this particular time it was actually powered down from like a transmission perspective, hence the red lights on there. Normally you would have kind of green operating lights on the transmitter, and yeah, everything would be hunky-dory on the 2 frequency hopping units as well. So the key thing is the reference frequency of the oscillator on the clock card is 13 megahertz. So 13 megahertz is a well-known kind of radio interface oscillator frequency for GSM and the evolutions of GSM through UMTS and LTE. And the reason is the 13 megahertz output can be divided by 48, which gives us 270.833 kilohertz effectively. I put kilobits per second here because that matches the actual line rate that we're actually going to transmit on the radio interface. If you remember, that TDMA frame had that gross data rate of 270.833 kilobits per second. And from that, we can actually derive a one-time bit, which is 48 clock cycles, or a 12 clock cycle quarter bit, which is actually the time unity used within a user equipment, or an MS as we called it in the days of GSM, a mobile station. So we've got a 13 megahertz clock reference. Now the original clock cards contained very, very high accuracy oscillators, because effectively they were standalone. There was no source of reference or discipline for the oscillator that was installed in the base station. So this is an example taken from some early Nokia training notes of the MCLU, this kind of master clock unit, but this is actually operating, as I say, without any kind of line reference. So effectively you've got 3 LEDs, the alarm, power and operation LED on the front, as we saw on the other cards. We've got a potentiometer here that says adjust, and we've got a test point here for the 13 megahertz clock. Now with this particular type of oscillator, effectively you had to visit the site every 6 months or so with a highly accurate frequency counter, typically with a rubidium reference, so they were quite expensive beasts. It took a while to kind of heat up as well and get up to temperature before you could actually do any kind of adjustment. And literally, as high-tech as GSM was, it all came down to an old trimming tool, effectively, where the actual potentiometer was adjusted to actually set the reading on the rubidium-based frequency counter to exactly 13 megahertz. And you would simply adjust the pot until that reading was correct. Now that would be a huge drain on resource, of course, because it had to be done every 6 months, plus the cost of buying the cards themselves with very stable oscillators, and the cost of buying a number of rubidium-based frequency counters as well. So the plan was to come up with an alternative technique of disciplining the oscillator such that the operation of the network could be stabilised. We would have no need to visit site regularly, and actually you could use a cheaper oscillator in a clock card if that clock card was constantly disciplined by some kind of reference that you had some confidence in. So the idea was to move away from the MCLU card to the MCLP. Now the P in this particular case stands for PCM, pulse code modulation. What it strictly means is a 2 megabit per second line. The 2 megabit per second line, as we'll see over the next few slides, is by design synchronous, because again that's time division multiplex based. And by using the 2 megabit line to provide a discipline for the oscillator, we didn't have the requirement to visit site. So therefore, once the system's up and running, everything is fine. You see here now we've got a 13 megahertz test point. We do need to take a reading on the card, but you no longer have the potentiometer to adjust it. If you need to do a fast tune, you can actually log in via the operations and maintenance unit and change the DAC word, the digital value, and quickly bring the card into frequency. So for example, when you're installing a new card or commissioning a new base station. So here we see now a diagram of that MCLP based card. Now the specification for the radio interface is 50 parts per billion, but to maintain 50 parts per billion on the radio interface we need an incoming reference that's accurate to 15 parts per billion, and that allows some budget then for movement within the base station itself. So the 2 megabit reference comes in carrying the Abis interface into the BIE, the base station interface equipment, and in particular into the DB2M card, digital branching 2 megabit card, on the DF12 base station. Obviously as base station generations evolve, that card type has changed. We've then got an OMU signalling link going through to the operations and maintenance unit where we've got the hardware database, and we've got a reference clock that feeds into a comparator and effectively a phase lock loop where the digital word value feeds that OCXO. Okay, so we've now got an oven controlled quartz oscillator in there, and the outcome is 13 megahertz, and we can keep that clock stable through this loop and the reference we've got on the E1 line itself. So why is the incoming line synchronous then? It's worth spending some time just thinking about this now, because we've kind of used the incoming 2 megabit line for many years now for synchronization, and when we moved away from 2 megabit lines we suddenly had a new challenge. If we're going to move from 2 megabit and TDM systems to Ethernet, we need to get synchronization into Ethernet as well. So let's first look at why this line is in fact synchronized, and then we'll see later in the presentation how we adopt some of these techniques in carrier Ethernet today. So the need for some sort of synchronization in telecommunications has always been there. It's either a case of you talk or I talk. Telecommunications has evolved, particularly over the last 50 years. The main need for synchronization has been driven by the adoption of pulse code modulation. And pulse code modulation was originally adopted as a transmission technology, so it was effectively used between switches to actually drive long lines. You don't get the same build-up of noise that you get in analog amplifiers, for example. You can clean the signal up at each regeneration point, and you can recover the signal very effectively at the end. So we've got an example, wonderful image here from BT Archives, and you'll see one of these racks of equipment in the Information Age Gallery at the Science Museum as well. To learn more about the history of pulse code modulation, there's a great series of books that were produced by Marconi Instruments some years ago. I picked this one up on eBay. They're generally available fairly cost effectively. There were 3 versions of this book made over the years, and this explains the story of pulse code modulation. Now, PCM itself was developed by an English engineer working in Paris at the time in 1937, a gentleman called Alex Reeves, and the technology was developed from a theoretical model. So actually at the time in 1937 it wasn't practically possible to realise PCM. We had to wait until the advent of the transistor and more developed electronics to realise PCM networks, but nonetheless the theory was established back in 1937. Now the GPO, the forerunner of BT from a naming perspective, so the company I work for, really did embrace the idea of digital transmission and actually led the world in the development of pulse code modulation systems to increase transmission capacity and performance on lines between exchanges. But actually it wasn't long after the introduction of PCM transmission that we saw the introduction of the first digital PCM based switch. So now we start to think about a transmission line coming in that's carrying time slots. So you've got a little piece of information in one time slot that has to be cross-connected across a switch and leave on a transmission line at a designated time slot again. So you've got the need for synchronization not only in the transmission but across the switch as well. And early digital switches often had a rubidium frequency reference on board. In fact, some of the very early ones actually had cesium rather than rubidium. So cesium tended to be deployed into the actual switch itself, so a very accurate, very expensive clock to guarantee that performance. But over time, again, developments in oscillators meant you didn't need to have a cesium reference on every switch, and in fact you could deploy a small number in your network and carry synchronization over the line. So the concept of synchronization as an art of telecommunications, as a technology in telecommunications, is very well developed. But actually it's not something that's understood by many engineers at all. It tends to be out there, it works, but when it goes faulty it can cause real problems, particularly on mobile networks when you start getting dropped calls and potentially even out-of-band radiation from base stations. So synchronization is an absolutely critical topic. So Empress Exchange near Earl's Court in London was the world's first fully digital telephone exchange, and that opened in September 1968. And then we actually developed that frame further to deliver a whole range of access circuits as well, where if we take an example here, we've got the frame from an E1 circuit, so 32 time slots, 64 kilobits per second per time slot. Time slot 0 is what we call a frame alignment word, a not frame alignment word. So this actually does frame synchronization, alternates between frame alignment and not frame alignment, so you actually get the correct synchronization. I've numbered 1 to 8 the number of bits in each 64 kilobit per second frame, because 64 kilobits is the basic building block of the PSTN, the public switch telephone network. However, as we'll see shortly, we used a low GSM and therefore modified the use of this frame. Time slot 16 is where we deployed channel associated signaling initially, and then that became common channel signaling over time with the introduction of things like signaling system number 7 or DAS or DPNSS type signaling schemes. But the old channel associated signaling system effectively used a 16 frame multi-frame to allocate 4 bits of signaling for each of the 64K time slots of 30 usable time slots, excluding time slot 0 and 16. So the photograph here is a dual shelf multiplexer. So this again shows the age. This equipment was used extensively in the 80s and early 90s. The top shelf is a common shelf here, and the bottom shelf is the actual signaling shelf. And each one of these cards can support 2 64K slots. So effectively 2 groups of 1 time slot on a card. They could support telephone lines, they could support data services, for example, that could be mapped into 64K time slots in our E1 frame. But actually from a GSM perspective, if we look at a typical Abis interface between the BTS and the BSC, then we can see it's quite a modified looking frame structure. So to take a moment to explain this particular diagram, in time slot 31 we deploy an operations and maintenance channel, and then time slots 30 through to 21, there's 10 time slots allocated for TRX signaling. Now this is the original DF12 model. TRX signaling over time did reduce from 64K to 32K, which allowed you to actually increase the number of transceivers that you could map onto a single E1. In some cases it also reduced to 16K, although from my experience that caused problems and was quickly pushed back up to 32K. So for a single TRX that we saw in the earlier diagram of the base station, we've got TRX1 occupying 2 64K time slots to support 8 TDMA time slots, so the time division multiple access time slots on the GSM radio interface. So if it was a single TRX, then this time slot on the radio interface would actually be a broadcast control channel, along with maybe an SDCCH, standalone dedicated control channel 4, and you would then just increase the number of control channels, particularly SDCCH, as you increase the capacity with more TRXs. Of course, you could have either an omni configuration or a sectored configuration as well, and that would impact the way you actually build the actual Abis time slot map. But the key thing is that on the backhaul here, we're using 16 kilobits per second of transmission for each TDMA time slot. So we mentioned before that an original GSM full rate speech channel was about 13.6 kilobits per second, and you can see how that would map quite comfortably with a few overheads into a 16K time slot here. And the diagram now just really explains the story through the network, and it shows the extensive use of that E1 frame, that synchronous E1 frame through the network, where we've got the actual connection coming in from the radio we've got the Abis interface. We're then coming out of the BSC on the A-ter. We've got sub-multiplexers and transcoders. And coming out of the transcoders, ultimately we're back to 64K alpha law PCM, which is what we actually switched through the original MSC, the original mobile switching centre. Again, like a lot of these things, they evolved over time and started to switch at 8 and 16K, so multiples of 8 effectively. But the original mobile switches were all really just telephone exchanges with some mobility features added in, so they switched at 64 kilobits per second. Example here of a couple of pieces of equipment used to build mobile backhaul networks. And because the E1 frame is synchronous, then we could map n times 8 kilobits per second from a number of interfaces onto, let's say, an aggregate interface, and then reduce the transmission demand from, say, 3 partially filled E1 circuits to 1 fully equipped E1 circuit between different locations in your network. And of course that changed the economics of the network, so it made sense to deploy this type of equipment in certain scenarios. 2 examples here, a Nokia DN2, dynamic node 2 megabits per second, and a Telecoms DAX, a digital cross-connect equipment, both of which were used in UK networks by a number of different operators. Certainly as an example, the DN2 was used by Orange, and the Telecoms DAX was used by Mercury 1-1, which became T-Mobile. Of course, these 2 companies then combined to become EE and are now BT. So, we've got our synchronous frame. Now, there's lots of words on this slide. I don't intend to read them all as such. I'd just like to point you to this paper, and I'll make these papers available as well for you to download. This was a paper written by a colleague of mine, Martin Kingston, who's a synchronization lead for mobile in BT EE. The paper is the need for synchronization in telecommunications, and it's from a special edition of the ITP, the Institute of Telecommunications Professionals Journal, which was based on synchronization, and I'll cover off a few more papers towards the end as references as well. I had the honour of being the guest editor for that particular edition of the journal, and I was delighted with the input I got from colleagues in industry to produce some great papers. But actually, through this explanation, what Martin comes to is the need for a filtering function and also a kind of synchronization distribution function. And he introduces the concept of the SSU, the synchronization supply unit. And I have a synchronization supply unit here on the next slide. This is an example of a Symmetricon SSU supplied by Kronos Technologies. This was installed in an operational switch site on the Orange network. And you'll see at the bottom we have a number of input ports. So these will ultimately be traced back to cesium clocks sitting within the network, and they sit in the transmission network, and they're actually equipped within the SDH infrastructure at the time. We then got the input selection, the oscillators and the output drivers. So the oscillators are these modules either side, then we've got the driver cards in the middle, and then we've got a large number of outputs, and they would go out to things such as remote base stations, local BSCs, any transmission equipment or SDH transmission that needed a local synchronization source, we would distribute from here. So you can see a large number of outputs being driven from this particular SSU. So we've now got our GSM network. We've moved away from manual oscillators to these 2 megabit per second linked oscillators. We've removed the need for manual visits, and the whole network's working perfectly fine from a synchronization perspective. Let's add some 3G and see what happens next. Well, 3G introduced a whole range of new concepts. Firstly, wideband code division multiple access, and secondly, ATM as a transport network layer. Now, the introduction of ATM was interesting because we had underlying transmission, which was still predominantly 2 meg based. So we had 2 meg E1s to base stations, and we started to build IMA groups, so inverse multiplexing of ATM groups, where we added several low speed links together to create a logical higher speed connection. But actually, introducing ATM and some of the techniques around ATM with SDH for high capacity backhaul, because we're now moving away from being predominantly voice centric as we were with GSM. We did of course have GPRS and some years later Edge, but we're predominantly voice centric. we're now moving into a more kind of data-centric world with 3G. So we have to increase the capacity on our networks. So if we look at a typical network for supporting 2G and 3G together, from a 2G perspective, we've got our BTS over the Abis internet interconnect to the BSC itself. The BSC in most cases contained the PCU, the packet control unit, which was the BSC's kind of architectural peer on the packet side for GPRS, although it was generally a plug-in module into the BSC. The exception to that was Nortel, who used a standalone ATM, a standalone passport. It wasn't ATM, it was a frame relay-based passport platform, which acted as a PCU for a number of BSCs and then handed off towards the SGSN. So we've got the GB interface towards the SGSN and the ATO interface towards the transcoder and rated action unit. Now, adding 3G to a base station meant we put a node B on site. So we've now got this new base station with the ATM interface over E1. And the RNC, well, they tended to be much higher capacity modules than the BSCs were. So where you may have had some BSCs distributed, different operators took different approaches to distribution versus centralisation, but even if the BSC didn't sit on a remote site like this, there would be some kind of remote aggregation site or hub site, transmission high site type node that would act as an aggregator. If it wasn't a BSC here, you'd probably have a DAX or some kind of cross-connect there anyway. So from a topology perspective, it's the same irrespective of the approach to centralisation versus distribution. But now we've got our RNC sitting in the core. The key thing is N times ATM STM1 as the primary interfaces. RNCs did have some E1s, but mainly most vendors had high order interfaces. And these were VC4 based. So it wasn't 63 VC12s multiplexed together, as you would do with E1s into an STM1. Yeah, this is the VC4, it's an ATM VC4. So you've got a mismatch now between the N times E1 ATM UNI interface or IMA and the interface here. So what are we going to do about that? Well, there's a whole range of solutions implemented. This is the solution that Orange deployed in the UK, and this is using the Lucent PSAC solution. This is an early photograph of a PSAC being installed on one of those BSC sites, which became known as transmission nodes. It's a particularly early image because you'll see here the two STM1 links are not physically connected to the card, so it was actually going through the commissioning stage at this particular point and being integrated into the network, so they would have been connected prior to live operation. We've got a number of E1 IMA cards here, so we're now supporting those E1 circuits coming in from the node B and aggregating them into the STM1 line as part of an ATM VC4. We've also got some multi-service cards here, taking the ATO and GB interface and actually emulating those over the ATM network as well. So we're building a truly converged 2G, 3G network. And you can see lots of balance panels here because to get this density on the cards, they used unbalanced 120 ohm interfaces. Balanced 120 ohm interfaces, whereas the interfaces here are unbalanced 75 ohm interfaces on coaxial cable, effectively. So we need to convert between the two, which we do via the actual balance panels itself. So 120 ohm balanced, 75 ohm unbalanced on the coaxial interfaces. But this breaks the actual simple E1 synchronization circuit that we had. So we've now got a challenge. How do we deliver synchronization over an ATM network? Now there are a couple of techniques for doing that. There's techniques such as adaptive clock recovery and synchronous residual time stamping, both of which through testing we found could actually result in problems when the load changed quickly in particular. So with that concern, we moved from this GSM synchronization architecture that we explained, so fairly simple, with a PRC sitting typically in the PDH network, evolved to SDH over time, clocks in the MSC, passed through to the BSC and passed through to the BTS, and all the transmission was E1 based, so it was that synchronous 2 megabit per second clock. But actually, in a converged 2G, 3G world, this looked very different. We've now got primary reference clock in the SDH network here. We need to connect to an ATM cross connect. But actually quite often this transmission here, this SDH transmission here, was delivered by a third party. So there's no guarantee of the performance on that. And particularly E1s carried within a transmission line were actually susceptible to pointer adjustments as well. So even though we're going to recover the E1s eventually, there's no guarantee of the synchronisation performance. So actually what happened was many operators deployed GPS-based synchronisation, but of course that could be susceptible to space weather incidents or GPS jamming. It was less prevalent back in the early days of 3G than maybe that is now. However, to back it up, the SDH line itself, the 155.52 megabits per second, is synchronous, traceable to a G811 clock source, and therefore GPS would be the primary, the SDH line would be the secondary source, and there would be a holdover which would actually be used as a worst case as well to keep things running. So that would be the hierarchy for the clocking into that particular ATM cross-connect, and that ATM cross-connect, in the example I gave, is this Lucent PSAX platform, and there were a whole bunch of other platforms out there as well from suppliers like Nortel, Alcatel, etc. From here we can provide an ATER circuit into the BSC, and then E1 transmission to the BTS, and again E1 or N times E1 out to the actual node B itself as well. So this part of the network is effectively the same as here. It's just E1 based. Complexity is introduced where we do the aggregation from here back into the core as ATM VC4s. The actual oscillator and GPS clock source that was deployed to site in the case of Orange UK was this Dayton GPS LC unit. Now Dayton had just been bought by Symmetricom at the time actually, which is why the module shows Symmetricom on the photograph here. You can see the bottom of a PSAX 2300. There's actually an Alcatel-Lucent STM4 MUX down the bottom here as well from the transport network, and here you can see the synchronization unit. So it's actually a module that would normally plug into an SSU type chassis, but actually the module was modified, mounted sideways on the back of a 2U plate to allow it to address this particular application. And you can see here the same connectivity just passed through the front plate that you have on the actual plug-in module itself. And that's then referenced to a GPS antenna, and here's an example of one of those installations on a transport node in the Orange network at the time. So let's now add some 4G. Synchronization evolves when we move away from E1 based transmission, because prior to the end of the 3G evolution with HSPA, we started to move from E1s to Ethernet backhaul. So IP transport in UTRAN was standardised back in 2002 in 3GPP release 5. So some years after that we started to see a migration, firstly to carrier Ethernet, carrying pseudo-wired E1s, and then to full IP transport implementation on the actual node B and the RNC itself. So we moved to IP on carrier Ethernet, and from release 8, the first base standard for 4G, we had that same principle of an IP transport network layer with carrier Ethernet. So we've got a true IP-based multimedia communication system now. An example here of a multi-band antenna supporting 4G along with legacy radio access technologies as well. But the key point now is that all transmission interfaces are carrier Ethernet. I use the term carrier Ethernet to differentiate from Ethernet as we would know it in the LAN environment today. There's lots of bells and whistles that we add into Ethernet to support transmission over the wide area network in this way. This is based upon the work of the MEF, the Metro Ethernet Forum. So we've got no TDM. We've got base stations that are increasingly supporting more than one type of radio access technology. The concept of spectrum neutrality has been introduced as well, where you can use different frequency bands for the most appropriate radio access technology. So we've seen GSM 900 used, for example, for UMTS. So the 900 MHz frequency is no longer GSM, it's now UMTS. We've seen GSM 1800 be refarmed to become LTE 1800, and those principles continue as we move forward. But actually we've also got support now for time division duplex in 4G. Now there was TDD spectrum in 3G, but it was never deployed for a number of reasons. So the first time we really come across TDD, certainly in Western Europe, is with the introduction of 4G. We've got techniques such as COMP, coordinated multi-point transmission and reception, where we need to guarantee time alignment between base stations to get coherent reception on a mobile device. We have co-channel small cells that need techniques such as enhanced inter-cell interference coordination. And we've got broadcast and multicast technologies as well based on EMBMS. So a whole range of new requirements now that not only need frequency synchronization, but also require phase alignment or time alignment, where effectively, rather than just having, if we visualize it as two sine waves, rather than having two sine waves on the same frequency, we need two sine waves that are not only on the same frequency, but start at the same instance in time. So 0 degrees, 90 degrees, 180, 270, 360 is completely aligned as that sine wave plays out. So, firstly, how do we address the frequency synchronization? Well, I mentioned before that some of the techniques associated with TDM and the E1 frame we would find ultimately in the carrier Ethernet world. And we do that through something known as synchronous Ethernet, or SYNC-E as it's commonly known. This was a specification developed by the International Telecommunications Union, the Telecoms division, where a physical layer sync reference was implemented on the actual physical transmission, so using the line code in the same way we do with the HDB3 on the E1, to actually recover a frequency reference. Now that frequency reference gave us the 15 parts per billion line accuracy that was required to ultimately derive the 50 parts per billion reference for the radio interface. And that reference will be delivered on an Ethernet interface. So here's an example of an Ethernet interface into a multi-wrap base station. So from a 4G perspective, that's carrying an S1 and an X2 interface, but it's also SYNC-E, so therefore we take the frequency reference in the baseband unit from that incoming circuit. There was another technique developed by the IEEE, known as 1588-2008, or PTP, the Precision Time Protocol, and that can also be used to deliver frequency synchronization by using a message-based system, so like a layer 2.5 type system, delivering messages which at the end would clock out synchronous Ethernet to a particular box. And that would be used in scenarios where you didn't have synchronous Ethernet equipment along a particular line. But also, the evolution of IEEE 1588 gave us the option of implementing time of day as well, or phase synchronization, which we couldn't do with SYNC-E. And actually a combination of using SYNC-E for frequency to stabilize the phase on 1588 is a perfect combination of converging the two technologies. Now from a phase perspective, we have to deliver plus or minus 1.5 microseconds on the radio interface, which means from a line perspective we're targeting a performance of around about plus or minus 1.1 microseconds. So again, we've got a little bit of budget to play with within the base station itself. And this would now be traceable to some form of UTC typically, so Universal Time Coordinated, so effectively time of day, and that would give us that phase or time synchronization. It also means we introduce a new node in the network, not just the SSU as we knew it before, but now a new PRTC, a primary reference time clock, where we actually distribute that phase synchronization signal to all the endpoints, the slaves that need to receive it and act upon it accordingly. So, to summarise today's presentation on behalf of the Cambridge Wireless Heritage SIG, frequency synchronization is absolutely essential to the operation of cellular networks, and it's essential to the operation of state-of-the-art 4G and 5G networks as it was to 2G and 3G. Advanced radio features are now putting more demands on the network in terms of demanding phase synchronization, so it's time of day synchronization, as well as just frequency synchronization. The synchronization network itself must be robust and resilient, because it really does underpin not only the network operation but also the performance of your network as well. SYNC-E and PTP are important network synchronization technologies to enable our mobile future. So those are going to be the technologies which will underpin delivery of sync and time in the future. 5G is a massive step towards the adoption of TDD, time division duplex, with many of the higher frequency bands being implemented as TDD. There will be FDD as well, but many bands, particularly the pioneer bands and the very higher frequency bands, will be TDD, time division duplex. Now, time division duplex better aligns with the nature of traffic today, which tends to be asymmetric, with much more downlink traffic from the network to the user than there is from the user up to the network. The original FDD, frequency division duplex, had symmetrical bandwidth in both directions, and that was really driven historically by voice telephony, which had 64K down, 64K up, and then you would multiply them up. But now we're talking about asymmetrical uplink, downlink, so TDD is well suited. But TDD does need phase synchronization. So we'll see more PTB-based line-fed synchronization, and I'm sure we'll also see more GNSS-based deployments. So that could be GPS, it could be Galileo, for example. So as radio access frequency bands increase to deliver ever higher peak and average data rates with lower latency and better performance, phase sync becomes ever more critical. So in a heterogeneous network with co-channel operation, again, phase sync is a key component there. And the illustration here, the photograph here, really does show the kind of density of users you could get now and some of the challenges we have delivering capability into these areas. I mentioned the ITP Journal, the Institute of Telecommunications Professionals. The URL is at the bottom here. This was a special edition that we produced on synchronization. I was a guest editor, and here's my editorial. And then we had 4 papers in total. We had the paper I mentioned earlier from Martin Kingston, The Need for Synchronization in Telecommunications, which is a great introduction to synchronization in both fixed and mobile telecoms. We had a paper from Charles Curry titled Time from the Sky, that looked at the development of GPS and taking time from the GPS satellite constellation and its evolution, along with some of the challenges as well associated with GPS and similar GNSS systems, and a little bit about potentially mitigating that through other wireless technologies. We then had a paper from Sebastian Gilbert and Kenneth Hahn talked about PTP, the Precision Time Protocol, that we talked about before from the IEEE, and how that's used for both frequency and phase synchronization. And then we concluded with a paper from Tommy Cook and Tim Frost from Calnex that talked about how do you actually validate the delivery and performance of synchronization through test and measurement. So, thank you very much. I hope you've enjoyed the presentation, and the slides are also available to download along with the ITP papers. Goodbye.